This is on the assumption, of course, that A by Z is much less than 1 in some sense. So, the norm on matrix A divided by scalar norm of Z, that defines your ROC, region of convergence. Let us not get into the fine details. This is expressible as long as this series converges, and that convergence is guaranteed by choosing a region of convergence. Once you have done this, then the inverse transform of this can be very easily written is equal to I plus Z minus 1A plus Z minus 2A square plus Z minus 3A cube and so on. Okay. So, inverse transform of this is what? X0 is a constant, mind you. So, I can multiply the inverse transform by constant to get actual value. So, inverse transform of this will be just equal to I plus what is this equal to? Delta minus and this will be 0, right? I must put plus 1. I A Z minus 1. This is right? Okay, good. Now, inverse transform of this will be, oh, you are saying, okay. Inverse will be I delta 0. Is that what you are saying? Delta n rather. A delta n minus 1 and so on. This into x0. So, the nth term in this or kth term in this will be just equal to ak, a to the power of k into x0, and that is the solution we have got for the ZIR in the time invariant case. So, matches. As for the time ZSR is concerned, then what do you get is ZSR part? Here. This is ZSR part, and this is nothing but convolution of the input This is the Z function multiplied by another Z function. The product of two Z functions in the sample domain is equal to convolution of these two. So, convolution of this, which is UK, with convolution of the inverse function of this. The inverse function of this, remember, again can be written because using this relationship, and that multiplied by B will give you what is the Z function corresponding to this, and another Z function. These two are in product. So, in the sample domain there will be convolution between these two. So, I get the solution for JS. So, you can go both methods. You can go directly in the sample domain itself like we did in the earlier just few minutes ago, or you go round, go to transform domain and come back here. In this discrete systems, I don't know, my opinion is that there is not much of an advantage for you to go into transform domain and then come back to original domain. Although there is a transform available to you, it is more easy to do it directly in the time domain itself, because the samples are some set of numbers. There are no integrations involved, there are just products and multiplication addition. So, there is not a big handicap for you to do it in the time domain itself. So I don't think you should do, but there's the beauty of the mathematics involved in this, the representation. So people try to talk about it. There is one more observation which Sayantan brought it to my notice. So let me complete that also. If you have Hn as the unit sample response, which is equivalent to impulse response, and if Xn is the input to this black box with H of n, and if Xn is kept as the input, then you get some Yn, which is by result which we got in the last class, is nothing but sigma k is equal to 0 to n minus 1 hk into xn minus k. Convolution. Now, when is this system stable? Okay. There is one stability criterion which is some kind of a limited stability criterion called Bibo stability, bounded input, bounded output. Okay, not Bebo, it is Bibo. Bounded input, bounded output. So, under what condition this black box will have this property of Bibo? There Bibo says that if the input is bounded, output should also be bounded. That's all it's simply saying. If the input is bounded means x of n must be equal to less than some x for all values of n. Then this has to be bounded now. So Yn must be bounded, and this is equal to bounding on this. This from mathematics you know is less than sum of Hn okay, bound is less than the. This is bounded xn minus k, that is assumption here. Any value of n that is bounded. So I can pull this out.
That has to be summation over xn. The first line condition, input condition, summation over xn is less than capital X.
X of n.
Summation over xn. Summation over the absolute value of xn.
That's what I am coming to. So this should be less than infinity.
So the first line, to satisfy this, the first line has to be summation over xn less than capital X.
This one.
Just next line. Summation over xn, that left side of that inequality, summation over xn.
I should put a sigma here.
Yes, before that.
No, not necessary. No.
Well, sir, for example,
The input amplitude is limited at any instant of time, or the sample values are bounded at any sample time.
sir, actually for unit step function, if we say
No.
un, that is not
Your step function is fine. Step function is fine because the amplitude is limited to 1. So it's always less than it is bounded. It has to be amplitude bounded. So I pull this x out, and then this must be less than bound. So since this is a bounded value, so the condition turns out to be sigma Hn must be less than infinity. Okay. So obviously, if you have a impulse response or the so-called pulse response of a black box like this, and if it extends from minus infinity to plus infinity, it is not obviously comes under this category, right? Because there are infinite number of them, and the summation of all this must be a bounded value. If it is only from 0 to n minus 1, that is a causal signal, but a finite causal signal, then only those sample amplitudes must add up such that the magnitude of the sample amplitudes are summation of them is less than infinity. So, any impulse response, sample response function of a finite causal signal, as long as the amplitude is limited, we will have a B-Bose stability. This is a kind of loose stability, right? B-Bose stability is a loose stability. It is not a strict stability. And what is strict stability? Remember your 101? A system is completely stable if the poles are located in the left half plane, strictly in the left half plane, no j omega axis allowed. Remember what is Z transform? Z transform is translating thereby a warping e to the power of s. So, the left half plane has become inside of unit circle and right half has become outside of unit circle. And you are not allowed to have any poles in the right half plane. And it is a causal signal. So, obviously, the region of convergence of the Z transform must be outside of the unit circle. If that is satisfied by the Z transform, then you are guaranteed that any input will give you a stable output. But that is not same as just a simple one here like this. The amplitude modulus must be finite, summation of that. That's why it's called a limited B-Bose stability. In fact, most of the time people are bothered about if this is an amplitude limited signal, do I get an amplitude limited signal? This is all the interest that people have. So, this is a good enough descriptor. In the next class, what we will do is, if this same black box which is specified h of n comes out to be gives you a y of n, right? I am assuming that the signals are, till now I am assuming signal xn is either a real signal or a complex signal. I have said it earlier, but didn't pursue too much of complex part of the signal here, but extension to complex input to complex output is quite a straightforward exercise. I am not going to spend time on that. So, deterministic, real or complex, we have all the techniques that we have done till now can be used for solving. The next question comes, if action happens to be random, the signal is a random samples, and since the sample value, this is a random variable basically, and this random variable only described by the probability density function, marginal probability density function as well as joint probability density function of that sample with other samples in the x of n. So, you have a very big joint density function corresponding to all samples in this, which is to be described. Once that description is given to you, h of n also can be random, because this whole system may be going up and down in a random manner. For example, fading channel, when radio signal goes in there, goes to a channel, and the channel may have thunderstorms or so many things, the properties of the channel changes. As a result of that, signal received at the other end goes on randomly change. So it's possible that the system also can be a random system. Then the doubly random system here, input as well as the system, will give you obviously some random output. The question here is, if I give you statistics on this, and for the time being, let us make our life simple and say this is a deterministic system, not a random system. Can I give the statistics of y of n? The most complicated problem is, given x of n in terms of this probabilistic description, joint probability, can I find out what is the joint probability of y given this h of n? Obviously, y and x are related through h of n by an equation, like we did last time in the case of a difference equation. So, from the difference equation, I should be in principle able to find what is the probability density function of nth order density function for y given the probability density function here. But this is a very, very complicated problem, and there are very special techniques I only mentioned in the syllabus, that is called a Fokker-Planck equation, and how to solve the Fokker-Planck equation is a very complicated one. So, I won't go into that, but I just want you to remember this problem does exist, that given the statistics of this prime probability statistics, I want to get the probability statistics assuming the system to be deterministic. There are techniques available, but I will not go into that, and the method is to use what is solution of a so-called Fokker-Planck equation. And so, I gave the name to you to remember somewhere here, so that someday in life when you come to word Fokker-Planck, you connect it up and say, yes, we heard about it. Beyond that, I will not go. But what is important to me is, if the signal is a stationary, Whiteson stationary signal, then if I know the mean of this, if I know the variance of this, and if I know the correlation function of this, how do these move or translated by this h of n to this y of n, and what is this mean value, what is this correlation function, and what is this variance in terms of h of n. This we can do very easily. So, this is what we will do in the next class.